Hi there! Meet Kevin and Carlos. They're having an interesting conversation. Kevin believes that your tone of voice can actually change your chances of getting a date. Carlos isn't so sure. He wants to see some proof. So how can we find out who's right? Or have you ever wondered how scientists and researchers prove their ideas? Whether it's testing a new drug, comparing teaching methods, or analyzing user behavior. It's all about hypothesis testing. In this video, we'll break down hypothesis testing step by step so that by the end, you'll not only understand what it is, but how to actually perform it. First, what is hypothesis testing? Hypothesis testing is a statistical method that helps us decide if there is enough evidence to support a specific belief about a population or any theory we could have. Let's start with Sir Francis Bacon, who was the person who refined hypothesis testing. Now we will see the elements that make up hypothesis testing. First, we have the null hypothesis. The null hypothesis, noted as H0, which says there's no effect or no difference. That's why we call it as null effect. Now we have the alternative hypothesis. While the alternative hypothesis H1 says that there is an effect or a difference between the sample and the population, but the null and alternative hypothesis are complementary, which means that if one is true, the other one must be false. But how do we figure out what the null hypothesis is? Let's say Kevin and Carlos switch topics. This time, Kevin claims that drinking coffee helps you concentrate. In this case, the null hypothesis would be that coffee has no effect on concentration, it doesn't help or hurt. It just means that nothing happens after drinking coffee. The alternative hypothesis is that coffee does have an effect. It could make you more focused, or maybe not. And just for the record, I love coffee too. Another important concept to understand is sample size. A sample is a smaller group taken from a larger population, basically, a small slice of the whole world. As shown in the image above, it's the small information we have that represents a much bigger population. For example, let's say we want to know the average age of children in a country. Instead of surveying every child, we take a sample, a smaller group, and use that data to make estimates about the entire population. Now let's learn about the cutoff score, aka critical value. The cutoff score is the critical value that marks certain areas of the comparison distribution used as a reference for tests of significance. And this depends on the tails. We're going to see more about tails soon in this video. Now let's talk about the alpha level, also known as the significance level. This is a really important concept because it helps us decide whether to reject the null hypothesis or not. In simple terms, the alpha level is the threshold for what we consider unlikely enough to reject the null. Common values for A are 0.05 or 0.01, meaning there's a 5% or 1% chance that the results happen by random chance of extreme 5% or 1%. If our results fall below this threshold, we say they're statistically significant, and we reject the null hypothesis. I'm going to leave this here so you can understand better. You can pause the video if you want. Now let's learn about one-tailed and two-tailed tests. One and two tails are closely related to alpha level due to the fact that alpha changes if we have two-tailed test. One-tailed is a directional hypothesis of the alternative hypothesis, which means it can be either right-tailed or left-tailed. The alternative hypothesis determines whether it is right more than or left-tailed less than. While the two-tailed test tells us a hypothesis that predicts a different from outcome and does not specify a direction of the effect leads to a two-tailed test because an outcome in either direction can justify rejection of the null. The next step, after choosing the alpha level, is to find the p-value and the rejection area. To do this, we use what we've learned about one-tailed and two-tailed tests. Then, we look up the corresponding values in a z-table or t-table, depending on the type of test. These tables help us figure out how extreme our results are and whether they fall into the rejection region based on our chosen alpha level. Consider that there are two possible outcomes. The p-value is either less than A or greater than A. Remember, Grantor samples will help us to identify significant differences in either direction. At the same time, the sample size will affect our p-value in terms of alpha level, which means that we can find some error during the process. It leads us to type I error. Rejecting the null hypothesis when it is in fact true constitutes a type I error. Another way of looking at it is that the outcome represents a false positive, and type 2 error. Failing to reject the null when it is in fact false constitutes a type 2 error. Another way of looking at it is that the outcome represents a false negative, and the level of significance of a statistical test also sets the maximum probability of making a type I decision error. And the probability of a type 2 error is represented as beta, which is kind of hard to calculate. Now the best part, steps of hypothesis testing. Step 1, determine the appropriate test to use. Step 2, state the claim and identify the null, H0 and alternative, H1 hypotheses. Step 3, determine the alpha level alpha. Step 4, identify the critical value of the test statistic. Step 5, calculate the test statistic. For this step, we can use these two equations, z-test and t-test. Step 6, compare the calculated test statistic to the critical value. If the calculated value of the test statistic is more extreme than the critical value, reject H0. Otherwise, fail to reject H0. Step 7, interpret the decision. Now let's go through an example. Imagine we have a sample of 100 children, and we want to test whether teaching them chess improves their IQ scores. Our null hypothesis would be that chess has no effect, meaning that it doesn't change their IQ scores at all. And the alternative hypothesis is that chess does have an effect, that children who learn chess at a young age tend to score higher on IQ tests. Now let's look at the data. Since we know the population mean, we'll use a z-test to analyze the results. Next, we find the p-value based on our chosen alpha level, in this case, 0.05 for a two-tailed test. Looking at the z-table, we know the critical values are 0.96. Our calculated z-score is 0.12, which falls well within that range. That means our p-value is higher than 0.05, so we reject the null hypothesis. There is enough evidence to say chess makes a difference. Thanks for watching the video.